Okay, so let's start. So welcome everyone. It's really good to see that we are more than 100 people to hear the lecture of Henning Müller. I will not say much. It's really a pleasure to have him here. I know him for maybe 20 years now from the previous life when he was doing image retrieval. So in the meantime, he discovered this new vocation on medical imaging, and he's been making a name for himself on this. And of course, his talk is quite interesting, and the subject is very relevant. So, Henning, just go ahead. We are looking forward to your presentation.
Perfect. So let me share the screen.
So for the people, if you want to ask questions, you can type them in the chat, but then you would also have the opportunity to ask Henning directly at the end of the presentation.
So do you see my my screen properly?
Yes.
Perfect. So first of all, thanks a lot for the invitation. So I'm really happy to give this presentation here in the AIDA Lecture Series, and also on behalf of the AI for Media project. And I will also take some of the results from AI for Media and also from another EU project called Excellence. So I wasn't really exactly sure about the people joining this talk, so I made it also a bit general and looked at like really what are the challenges for machine learning using medical data. As Nico said, so I've worked on medical data actually for quite a long time. I think I started in the late 80s to analyze medical data, and so it's really been something that I've been involved in for a long time before I did my PhD in computer vision. And this image here shows also some of the things that we've been working on. Let me see, I can take because we've been working a lot on like using text and image data combined, and using that to actually train models to look at what we have here, like an ontology mapping things from text onto the ontologies and using that then for the learning. So that is also something that I will talk about, and that is part of like the advantage, but also some of the challenges of medical data. And I have a little bit of a background about myself, just to say that I've actually been in between the medical world and the more machine learning, computer vision world for most of my professional life. So I'm a professor in radiology at the University of Geneva and a professor in computer science at the HESSO in Sierre. And I've been moving around between hospitals and computer science faculties. And most of the people actually ask me about where we are. I'm in Sierre, so that's here, and most people in Switzerland might know Geneva and Zurich, and this is actually Milan in Italy. So about the same distance from all of these points. And I think the most famous mountain in Switzerland, the Matterhorn, is about 30 kilometers away from my office. So really, we're really in the middle of the mountains. It's a very small town, but it also has a very interesting environment because we as a small school, I mean, we collaborate quite a bit, both in Europe, but also within Switzerland. So what I will talk about is a little bit about like status of medical AI. So there's a lot of talking about the quality of medical AI, the impact it will have. I mean, there's been a hype around it, but there are also many challenges. And so I will address challenges. I will highlight them a little bit, talk about some of the work we've been doing to leverage some of the challenges, but there's also a lot of things that that remain open. And in the end, I'm also very happy to have a discussion and your feedback and questions about that. So we'll put a link here, so I will make the slides available as well. So that's Geoff Hinton in 2016, so 6 years ago, talking about radiology. And basically what he said is that radiology is over the cliff. We should instantly stop training radiologists because we don't need them anymore, because within 5 years, all of them will be replaced by deep learning. The video is on YouTube, so you can watch it. It's quite interesting to see. But one of the things I think we've all seen retrospectively is actually that didn't happen, because there's very few tools that are actually used inside hospitals. So there are many tools that are available, that are certified, that could be used, But in routine clinical use, there's actually a very small number of tools, despite all of the predictions, despite, I mean, much of what we see when we look at the literature. It took some of the things just from the web. So, I mean, digital diagnosis, machines are better than humans. And there's a variety of similar things that are published in like Google's DeepMind. They were better than physicians in breast cancer screening. They also had something similar to eye scans, like eye fundus images. But there's also a lot of like hype exaggeration, and we need to really separate these things because the medical domain is quite complicated in a few things, in that it has a lot of diversity. We're hitting on a moving target because machines change, the ways images are produced change, clinical guidelines change, medical knowledge also changes over time. And what people started to realize is actually, even though many things work really well in a lab, when you try to adapt it to real life, when you use it in a clinical setting, so in a prospective trial, for example, actually things might not work in the same way as expected. And like model performance versus impact are really two different worlds that we need to look into. And also, even though AI sometimes outperforms physicians in specific tasks, patients would actually not want to be treated by AI. They want to have somebody to talk to and also to discuss their case, because it's not only about pure AI, it's not only about pure performance diagnosis, but many decisions can be taken in many different ways. So the type of treatment, if you have cancer, I mean, you can have radiotherapy, you can have an operation, you have chemotherapy, immunotherapy. So even though the number of treatments might be limited, it also depends on the particular situation of a patient, comorbidities. It might depend on what type of quality of life they are looking for. I mean, so it's not like like really a classification task, but there are many, many factors to take into account. And that actually makes life often quite difficult for running real medical AI in a clinical setting, integrating it into clinical workflow. I also put up this webpage, AI Myth, because I think it's quite important for all of us working in machine learning to pay attention to what we promise, what we talk about, and because the public often has a very different view of what artificial intelligence, machine learning, etc. actually is all about. And quite often when we search the web, we might have like humanoid robots. When we type artificial intelligence in Google Images, I mean, that's usually what we get. That's what people think about it. And I think we really need to check to separate what is like myth and what are really facts in this work. So when we look at medical data, I mean, there are many advantages of medical data. Medical images, I will mainly talk about images and images linked to structured data and text that we use, because that's mainly what I work on, what our team works on here in CL. And the advantage is that images are often created under fairly standardized conditions. So if you break your leg, you will have a specific view that is taken of the images. If you have a problem with your heart, I mean, you might get a chest X-ray, and it's taken under very standardized conditions, the same views. We also always, when we have images in a hospital, so images that are a part of a clinical record, so we know why the image was taken. We have metadata on the patients, like age, gender, comorbidities, etc., etc. When we know why an image was taken, I mean, a chest X-ray, you can take it because you have a heart condition, or you can take it because you have a problem with your lung, and then you know where to look at. I mean, you might have secondary findings, but if you look at the heart, even if there's a tumor in the lung, it might not be a problem. Maybe it's treated, it's taken care of. Maybe it's something that is old, that is not any problem anymore. But this is what we have on the patient. We have then a report describing the image for other clinicians who usually take a decision, for example, on the treatment of the patient, and then evaluates whether the treatment is working. So we often also have a temporary information for past cases on whether the treatment worked or not. If we have cancer, we often have survival time, we have disease-free survival time, and all these things we can actually use and feed it back when we try to learn. there's also much medical knowledge available, and it's often coded. So there are many ontologies that are maintained. In the US, for example, the National Library of Medicine maintains the UMLS, Unified Medical Language System. It's a meta-thesaurus that includes several ontologies, and that's very regularly, frequently maintained in that respect. And there's a lot of research, and I took this report here. It's called Riding the Wave. It's a white paper from the European Commission. I mean, it's 12 years old, but they estimate that medical imaging is occupying 30% of world storage. I mean, that's a massive amount of data. And when I look at what hospitals produce, I mean, at least for the last 25 years, it's been increasing almost exponentially. More images are produced. I mean, thinner slices, all the tomographic images, you can have tens of thousands of images for a single case. Or if we look at histopathology, it's very large images, 100,000 by 100,000 pixels. And again, if we have a tumor, it's cut into pieces. So you can have 20 of these slides for a single tumor for a single patient. And then when we look at some of the challenges, I mean, what first comes to mind is data privacy and ethics, because that can have limitations in terms of sharing data sets and making them available in terms of acquiring data. Whenever we acquire medical data, even if it's stored in an anonymized way, we need to make an ethics request, and that obviously can slow us down because it also defines what we can do with the data and what type of data we can actually acquire. So if we want to have additional data, if in the course of analyzing the data we have new hypotheses, we need to write an amendment. So that can slow down. Then medical equipment actually changes over time. It can also vary across hospitals. So the same CT scanner installed in two hospitals might actually produce different images because it's not configured in exactly the same way. And then if we look at large hospitals, like the hospital in Geneva, where I part-time work as well, there are, I think, 7 CT scanners, and they're renewed every 5-6 years. So basically every year we have 1 or 2 machines that are changing. So if we want to learn a model, we really need to take into account that we actually have changing data. So we're hitting on a moving target, and we really require a continuous learning on that. Another challenge in medical data is that pixel level annotations are extremely expensive. And we need specialists. Like if you want to classify tumor tissue in histopathology images, it's very difficult for a non-specialist to actually say what are the, on a cellular basis, what are the modifications that would lead to a grade 4 or a grade 5 in terms of a cancer, for example. And A, specialists are expensive, but B, often they're not available. It depends on the countries, but in Switzerland, it's quite difficult to actually have people annotating data, in addition to it being quite expensive. And when we look at image data, I mean, we have a tendency to focus on images, but it's part of a case. So we have a lot of information about the same patient. So we have a patient history, we have environmental exposure, other diseases, other risk factors, genetics, microbiome. I mean, there's a variety of very varied data that we have, and often temporal data. I mean, often temporal data, so the sort of the trajectory of a patient is often more important than absolute values. I mean, if you have your temperature, like a body temperature, if you have a fever, depends on, is it increasing, is it decreasing? I mean, this is more important than the absolute values of it. And when we look at images, I mean, the regions determining a decision are sometimes very small. As I said, for tumors in histopathology, we might have 20 images of 100,000 by 100,000 pixels. So it's billions of pixels per images for quite a few images. And then a small region of maybe 20 by 20 pixels could be determining the grade of the cancer, because the most severe region is in this case taken into account. And that is what actually might determine the treatment. And if we look at deep learning, I mean, deep learning has really changed many domains. I mean, radiology, histopathology, basically everybody applies deep learning. But to make it work well, we actually need a very large amount of data. So we need solutions that are scalable. And if we want it to work in not a single hospital, but across several hospitals, we also need diversity in the data, because we have these differences in the data creation. So in histopathology, we have different staining procedures. We have tissue thickness that varies from one clinic to another. We have different ways of preparing the tissue, but also in radiology, we have different machines, we have different machine parameters, different clinical guidelines. So if we want it to work in a different hospital, we need diversity to make it generalize. And another challenge in medical data is that the data are very unbalanced. So quite often, I mean, if we have screening, for example, very high risk cancer patients for lung cancer screening for very, very heavy smokers, we might have 1% of the people who end up being positive. So we have these unbalanced. So for machine learning, obviously, what we would like to see is that all the classes are equally balanced. But in a clinical setting, many cases might actually, even in a large university hospital, you might have 1 or 2 cases that occur. And often, if we have like laboratory machine learning algorithms, we take the most frequent cases and we discard the others. But they do occur in practice. And when they occur, I mean, we want them to be recognized because often they require a different treatment. But if we have very few cases, it's obviously difficult to train an algorithm to detect them. As I mentioned, we need continuous learning because we have changing equipment, we have changing clinical guidelines, and half-life of medical knowledge is actually, it's estimated to be between 5 and 10 years. So within 5 years, somebody leaving medical school, half of what he learned might be considered incorrect. That means that, I mean, the way that people are treated, the way that people are taken care of actually completely changes because of the increase in medical knowledge and the ways that these guidelines are done. And mentioned pixel level annotations are not available, expensive. We need to combine multiple sources. So quite often it's structured data. I mean, age, gender have a strong influence on decision making. I mean, if we look at COVID, male and female persons don't have the same symptoms. They don't have the same expression of long COVID, for example. And if we don't have that data, if we look at only the images, for example, that's something that we might miss out on. And if we really want an integration into clinical workflows where a clinician can take an image and an AI algorithm and the outcome and integrate it into the decision making, we also need to explain how this decision was reached. And again, I mean, there are many examples of like scientific challenges. For example, there was one, I think, a challenge on melanoma, so skin cancer, where we had cancer versus non-cancer. Many of the cases look quite similar, but then all of the cancer cases had a little ruler because they actually measured them. So that means the algorithm was not actually looking at the melanoma itself, but it was looking at detecting a ruler in the images. So the algorithms had a perfect performance, but not for the good reason. And if we have these biases somewhere in the data, we need to be able to find them. For that, we need to have some tools that explain the outcome of what we're doing. And many of these things that I'd mentioned, we try to address them in an EU-funded project called EXAMODE that we coordinate, where we actually have 7 partners. We have 2 academic partners, one working in images, one on text. Same thing for the industrial partners. Then we have 2 hospitals who actually help with the implementation of the decision support tools. And underlying, we have a national supercomputing center in the Netherlands that actually helps us to go up to scale. So if we look at some of the challenges that I mentioned, first is image accessibility. So getting access to data has long been a problem in medical AI. But actually, many of the funding agencies have changed their policy. So the NIH has been pushing, I think, for the last 20 years that all publicly funded research has to make data sets available. I mean, it was sometimes people say like, oh, it's difficult and we have ethics constraints, we're not allowed to make the data sets available. That's one thing. But with NIH pushing, many data sets are now becoming available. The repositories like TCIA, the Cancer Imaging Archive, TCGA, the Cancer Genome Atlas, that actually make thousands of data sets available. So browsing them, if you're working in a specific domain, it's definitely worth looking at these repositories and also at scientific challenges, because there's a very large body of images, of attached data that are available. And that's usually also where we start from. Even if we work with a hospital, we try to download all of the image data in the same domain. So we can actually start with these because some of them might be annotated and use that for our tools. And then we also have the biomedical literature. I mean, it's, as I said, many resources in the medical field are actually very well maintained by the National Library of Medicine in the US, or National Institutes of Health. And they also maintain PubMed, which is a repository of medical publications. And PubMed Central is the part of publications that is publicly available. So that includes all of the open access publishing, but also everybody who's funded by the US government. They have to deposit all publications also in non-open access journals in this repository to make them available. So the publicly funded research becomes available. And it's also an exponentially increasing amount. I mean, here I took the number of articles that are published per year, and we can see, I mean, the numbers are up until 2018, but I can assure you that it has continued in pretty much the same way. And this is, I mean, it's a very varied repository. It doesn't have the full resolution images you might find in clinical archives, but it's publicly available, and it has a lot of variety that we can use. And as I said, one of the big advantages here is actually that the rare cases that occur very infrequently in hospitals, this is actually what people publish about. So the medical literature is actually a very good starting point to find images of specific rare diseases or things like that. Because frequencies, as I mentioned, of cases or classes that we would like to classify data into are extremely unbalanced. It said, like in very high risk cancer patients, like lung cancer, smokers, very heavy smokers, it's less than 1% that are positive per year. And that's also why accuracy in many of these cases actually doesn't work. We need to check how we can actually evaluate it. And often between false positives and false negatives, there's also weighting that we need to apply. And quite often, if we look at COVID, I mean, missing one COVID case, so false negatives, so somebody who's not detected, this person might actually infect a very large number of other cases. Whereas if we have a false negative, so a false positive, so somebody who's negative but is marked as positive, I mean, for the person itself, he might quarantine, but at least there's no like domino effect where other people get infected. So the weights for these it's not necessarily the same. That's why sensitivity and specificity depends on the scenario where we look into. And I mean, so we've started to look into the medical literature. We've analyzed it particularly for histopathology images. I think we had the last download we had over 20 million images, many charts, graphs that we can remove, but also quite a few like compound figures, so we can actually cut them apart. Often we have separate figure captions that explain what is in which of the image, but then we have lookalike image. I mean, this is actually a drawing of a histopathology image of the cells. This was classified as histopathology. You can see that the structure, the texture, the colors are very similar, but it's not at all what we would like to see. So to make these images usable, we actually have set up a pipeline, and you can download the repository. It's publicly available. It's an FTP server. I think there are like 5 or 6 million articles that we can download. We can then extract the figures in the text, and we can then classify figure into figure types. We created actually a hierarchy for that, for all the different figure types that occur in the literature. And there are many images classified into these that are available, for example, in the image clay benchmarks. So this works very well. We can detect compound figures. We can cut them apart. Again, tools are available. Many of them are open source. So if you don't find them, you can contact me and I can share them with you. And then we have some metadata that are available for the biomedical literature, which actually determine whether tissue is human versus animal, specific organs, specific diseases. So here we have to then look into also the text analysis, the semantic analysis, in addition to analyzing the images. But like that, we can bring down the data set to something that in the end becomes usable when we have a limited number of false classification. Advantages, as I said, we have the rare images, the unusual, untypical ones, because that's what people publish on. So we can have a critical mass on these cases. We have many laboratories, thus variability, which allows us to, at least in theory, increase generalizability of the models that we learn. And we have an exponentially increasing content that also allows us to use, like, if we have novel equipment, if there's a novel CT scanner that comes to the market, this is what people would publish on. So we will have these new images that are added to a database regularly. So if we do a continuous learning, we should also be able to adapt to that. And this is just like to give you an idea of diversity in medical images. So these are the main organs in the abdomen, and we can see there's a lot of variability in humans. I mean, you have some people have small lungs, small livers, others have large lungs, large livers. The organs are theoretically almost in the same place, but there's obviously dependency also in that respect. And I mean, these are all cases that are relatively healthy, so there are no major diseases in the organs that are shown here. And another problem is, as I mentioned, is the image production in the hospitals. And I mean, I might need to explain what is radiomics. So radiomics is a field in medical image analysis where basic characteristics of the images are taken as biomarkers, mainly similar to genomics. So you have biomarkers that you extract from the genetics of a person. Here we extract biomarkers from most frequently tumors that occur. And the idea is then to use these basic features like color, texture features mainly to predict, for example, severity of a cancer. So we can predict survival time, cancer-free survival. We can also predict response to therapy and similar things. So that is something that we had worked on also for a couple of years. But one of the problems that we saw is actually that different CT scanners that are often used to produce the images actually produce quite different images. There was a study in the US where they took a basic phantom. So they cut like 10 different types of solid things in different densities, put them into a scanner, and then we could see how different CT scanners actually produce the images. And what we saw is that it's actually very trivial to detect which producer does. I mean, there are 4 big producers of CT scanners, and from the pixel data, we can instantly say, oh, this is a Philips, this is a Siemens, this is a GE scanner or a Toshiba scanner, because they use different algorithms in doing noise reduction, etc., etc. But that is a problem when basically the type of scanner you're scanned in changes the features that are then used to say, oh, this person is being operated, this person gets chemotherapy, and this person gets radiotherapy, for example, because obviously we want this to be fully reproducible. And I mean, also here we can use deep learning, so we can actually use adversarial training to remove the texture features to features that are totally invariant to the scanner producers. And here we can produce something that with the same patient would actually have exactly the same results on different scanners. And I mean, we had these phantoms that are just pure like tissue types that were cut out of like different materials, but that doesn't correspond to really what images from a human look like. But putting a human into 10 different scanners we cannot do because we expose them to radiation. And so one of the things we wanted to look into is actually analyze what are the parameters that actually change the images. So when we look at the CT acquisition parameters, and we have radiation dose. If we do screening, we want a very low radiation dose. If we want to do planning of radiotherapy, well, we want like a lot of detail, we put a higher radiation dose because we want to have a lot of detail. So images are produced with very different radiation doses. We have image construction parameters. We have construction kernels, something that you can see here, and some of them are like more like low pass filters, other are more like high pass filters, but they produce very different images. And we have different slice thicknesses, we have overlap. This is all a reconstruction thing that we can either do the production of the images or when we create the images from the raw data at the CT scanner. But we need to, when we want to do a retrospective clinical study where we compare these, we need to be sure where the images are created from, because this variability has an influence on the analysis and the comparison of features. And we want to make sure that any study we do, we actually compare images that are completely comparable. And in Switzerland, we ran a study where we took actually this this machine here, and let me see, can I? And I have a little animation here that shows this is actually a 3D printed phantom where we used human data that were publicly available. And it looks like a solid block of plastic, but actually inside it has different densities. And that allows us to then scan it. We scanned it in, I think, 7 different hospitals, so all university hospitals and 2 large other clinics in Switzerland on over 20 different CT scanners. And also for anybody interested, so we're in the process of making this data set available, because you can really see what are the differences in the features that are extracted and how we can actually treat them to bring everything down to somewhat like regular data set that we can compare in this respect. And we did a variety of analysis. Fortunately, the regions that we annotated, they're fairly homogeneous, so we can see that normal tissue is quite closely together for similar scanners. With one of the keys, there was a bit of a variability between different scanner producers, but most of the classes were actually quite similar. And we then analyzed also stability versus discriminative power of classical radiomic features with specific texture features we use, and also deep learning based features, where we can see what actually works well, so which are the features that we should actually choose for this type of studies. And as I said, one of the challenges is not only the variability in the data itself, but it's also sometimes reproducibility. And there's an initiative called the Image Biomarker Standardization Initiative, or Ipsy, where they actually looked at visual features in radiomics, and then they invited research groups to participate, extract features from images that were standardized, so everybody was getting the same. And surprising, but even like features based on co-occurrence matrices didn't get the same results. So they when then back checked what caused these differences. They actually sent patches also to MATLAB, because some of those features were quite different in MATLAB compared to OpenCV or like other Python-based tools. So the idea is really to standardize this. So whenever we use these features, we get exactly the same results. And the first one is finished, it's published. The second one is currently underway. It's about filter banks. And the third installation, we're currently starting looking into deep learning based radiomics features. As I said, continuous learning is something that I would really like to work on, but so far I've never had a data set that would actually allow us to do that. Well, we do have these changes in images. And this is a paper that I put at the bottom here. It's a paper from the Medical University of Vienna, where they actually looked into updating a data set, so you get new images regularly, also from new scanners. And then a radiologist would use an AI tool and would then say, oh, this worked well, this didn't work well, this we use for the report, and adapt the algorithm. One of the things that they realized in the first algorithm was actually that sometimes they were what's called catastrophic forgetting. So they modified the model too much, and then some of the older cases wouldn't work at all anymore. So something that worked at some point. So when we modify a model, we really need to pay attention that we're not forgetting things that were learned beforehand. But I think there's a lot of work to be done in that respect. And then in this project XMode that I'd mentioned, we downloaded publicly available data, and then we had 2 hospitals where we acquired over 20,000 cases as well. It's whole slide images. So all of these images are 100,000 by 100,000 pixels. So that's millions of patches if we cut them apart and then classify them. And here, in most of the cases, we have reports and images. First of all, we wanted to become independent from manual labels. So we had a small manually annotated data sets that we started with. And so this data set we then used to train a teacher model. we had a lot of unannotated data, or some weak labels, global labels, that we then used to create pseudo labels, train a student model, and then we could fine tune it with the manual labels at the end. And that actually led to very good results. But now getting to the image that I'd shown at the starting page, we actually wanted to completely get independent from the manual annotations. So here we then looked at the reports. So we looked at what are the classes that are relevant for the annotation. We extracted them from the report, mapped them on an ontology, took the images, put them into pixels, removed background, etc. And like that, we had automatically generated labels. We took those we had the highest confidence. And again, this actually led to really interesting results. So we had a fully automatic pipeline once we had set up the data and the classes, where we then labeled thousands and thousands of images automatically based on the reports, which led to very interesting results that with tens of thousands of images actually generated results that were very similar to the best results that we had obtained beforehand with a limited amount of manually labeled data. So that was one of the main findings. And again, it was published actually this year in July. The paper will detail some of these results in a Nature partner journal. And there was also a long discussion in the blog of the journal about that. Now, getting towards the clinical workflow and AI. So when we look into the clinical workflow, we have a clinician who has a patient who orders an image, and then the specialist who produces the image, views the image, writes a report that goes back to the physician based on a question and usually an anamnesis. So we have data on the patient, the environment, prior diseases, often genetic blood tests, etc., or development of a specific condition. Then the specialist usually needs to do differential diagnosis. So he explains what is most likely the diagnosis and what are the probabilities for a few related diagnoses that could also be possible under a lot of time pressure. So people work very quickly. They see hundreds of images a day, sometimes thousands of images a day. We have like tomographic images, for example. And if we want to use AI tools, I mean, A, it has to be fast, and B, it has to be integrated into this workflow. You don't want to start a new application, uploading the images, running the analysis, etc. But it really needs to be integrated. You don't just want to get a label, but you want to have evidence that you can add to anything you have. You also want to identify what is possibly bias, uncertainty in the information that you're having, because you want to explain the decisions and their context. And basically for this reason, we started to look into interpretability of deep learning, because we had very good results with our deep learning tools. I think 5 years ago, we looked into these interpretability. Much of what was available then was like heat maps. I mean, like guided back propagation, similar tools. I mean, there's a variety of tools that are available, GradCam, etc. To make sure that we can explain why the decisions are sound, that we find why something might not be working. So we had places where really the heat maps were not at all in the areas where we expected them to be. So they were not in the right organ. I mean, sometimes you have diseases, some organs bend or completely change shape. And that means that actually some of these changes are systematic, but we still need to make sure that we can actually identify why a decision was taken, so we can reproduce them, we can explain them, because we have a high impact of wrong decisions. And that's where we started with. In the AI for Media project, we actually went one step further, and we wanted to look at like all of the different terms that are around explainability, interpretability, transparency, accountability, fairness, bias, opacity, reliability, robustness, uncertainty, confidence, etc. Because there's actually a fairly big change also in the legal domain. So that's something that was done in AI for Media, where people analyze the legal situation. And there's actually, you have a right to have a decision explained. I mean, if your bank refuses to give you credit, you can ask for an explanation. And that's different from a few years back when that was not possible. And it's actually difficult quite often for algorithms, because many algorithms, I mean, how Google places advertisements might use thousands of features, and it's a mix of these features, and it's not one of those things that dominates. So that's why this actually modifies also the way that people use this information. Again, the outcome of the workshop was published. There's a web page where the presentations are available as well. So there's a lot on like GDPR, General Data Protection Regulation on the EU level. There's an AI policy. I mean, so it's also something that moves quite quickly. But I feel that this field of interpretability, explainability is really important to really give a position to AI of how to use things. And won't go into detail, but this is the link between the different sciences, between law, the technical sciences, cognitive science, sociology, philosophy, etc. And I mean, you can have a look at the paper. One of the tools that we developed in our lab is called regression concept vectors. It's basically based on the concept activation vectors that Ben Kim developed for classical images, which had binary concepts. For example, the zebra likeness or tiger likeness you can have in an image. And in the medical field, often we don't have like classes, but we more have like a regression part. So we have enlarged nuclei, for example, in histopathology image that give us an indication of modifications in the data. And or heterogeneity at the borders, but it's not like 3 classes of heterogeneity, but it's really a regression task that we took. And these regression concept vectors allow us to explain the decision of a deep neural network based on features that clinicians actually use. So we can say we can explain, I don't know, 30% of the decision making with these features, and then we know which features are positively or negatively correlated with it. We can also use it to actually make the results better, because one of the things we often use is that we use ImageNet pre-trained models for medical tasks. We then fine-tune them because we often don't have enough data available. Problem is, everything you do on ImageNet, I mean, it has a scale invariance, because when you look at the training data, I mean, every object, or most objects you have in different sizes. If we look at the features we have, I mean, scale invariance is exactly what we not want, because enlarged nuclei is actually a clinical feature. So that's why we actually pruned that part. So we removed part of the network and retrieved much better results. So by understanding which part of the network is responsible for specific things and which features we would like to see or we would not like to see, we can actually improve the outcomes that that we're having. And then also worked on different parts of visualization with a group that developed a visualization method called LIME and adapted it for histopathology with a variety of visualizations. Then gave that to clinicians to say, like, how would you like your decisions to be explained? And often people have like rather large or broad concepts and blocks, and not so much these heat maps that can sometimes be very good in explanations, but sometimes it's very difficult when you have heat maps all over the image. It's actually not easy to see. And I mean, we only did a very small user test in this part, but all of you who would like to work on medical data, I mean, plan that in, take some time so people would actually use the systems. You're not just running scripts and in the end get something on retrospective data, but actually looking into how humans could use it and how they can make use of it, because then you can also measure possible impact. But it's not necessarily easy. I mean, maybe clinicians with the use of tools can take better decisions. So there's some evidence of it. I put here a link also to a tool in radiology that shows that I think deep learning had a 90% accuracy. Radiologists would have 92%, radiologists 96%, and together they had over 99% in a specific task. But it's important to look into what we would like clinicians to do. Do we want to have better decisions, like better diagnosis, maybe also more confidence? Sometimes clinician might take a right decision, but maybe he's not very confident in the decision, which might then also influence the way they react to the treatment of the patient. Would they be faster? Maybe it's also a question of satisfaction or being less tired in taking decisions, because sometimes people actually need to take books, need to compare things to take the right path. And then the influence of the patient is also something that we can look into. So do we actually get a better treatment? I mean, sometimes we differentiate between 5 diagnoses, but 3 of them are treated the same way. So the question is, does it actually make sense? Do we need to separate the 2? Often clinicians don't do the separation because they feel like it's treated the same way. I mean, if you're in the peak of the flu season, I mean, nobody would usually do a flu test because you assume that it's mainly the flu, but everything else that's virus related might have a very similar treatment. So in that respect, it doesn't actually change something. And getting towards the end, I just want to say a few words also about scientific challenges. I like this image here. Where often people compete, and I think it's good to sometimes look at how to optimize results, but we also need to have a cooperation. And many of the scientific challenges are set up as competition, but I'd rather see it like as a co-opetition. So where people collaborate in finding better ways, in finding better solutions. And I think many platforms, I mean, Kaggle is maybe the best one known, but there are many other platforms that are available where medical data sets are available. And where particularly, I mean, if you're a PhD student and you're looking into comparing your tools with others, you would have strong baselines. You can check with other tools. I mean, it's not only about pure outcome, pure classification performance. It's often also about the interestingness of approaches. And many of these challenges can also be run without sharing confidential data. So only training data are released and shared, but then test data could be available by uploading a VM or a Docker container. So there are several platforms that allow that. And there's a lot of work in optimizing also scientific challenges in medical imaging. There's an initiative called BIAS to really document everything that you need. There's a couple of tools on like what are problems with metrics. We developed, this is available on Archive, a classification of what metrics to use when and also why, and what are limitations, shortcomings of specific metrics under specific conditions. And you can actually optimize depending on the metrics that is used. If you use, I don't know, dice score for segmentation, it's better to over segment than to under segment if you want to have a good performance. And all these kind of things, at least make them visible, explain them why something might be best practice in specific domains. And then, I mean, one thing that is also different for medical software is that medical AI actually needs to be certified for clinical use, for routine clinical use. So there's the CE label or the FDA approval for Europe or the US. And so unless you work on it for research study, I mean, you can work with uncertified software in research, but otherwise it has to be certified. This is quite a tedious process that can take time. And it's also gotten more complex for like in vitro diagnostics, so which AI tools would be if you do diagnosis for it, for example. It's expensive to do, so quite often research tools, even though they might work fairly well, it is not something that would necessarily be directly usable in clinical practice, because you need to have this step where actually all these approval mechanisms, they actually want to avoid any risk for a patient. So you need to document what happens under what conditions to really make sure that there's never anything that could be problematic for a patient. And I mean, I went a bit fast over the last few slides, but they're available. And if there are any questions, I mean, don't hesitate to ask them. I think what I wanted to show you is that, I mean, there's a lot of work to be done, a lot of research to be done. It's an extremely interesting domain with potentially very high impact also on people's lives on how to bring forward specific tools in this domain. Many challenges remain. I mean, some like data accessibility, I think it has gotten easier to address them, but many of them, like continuous learning, I think need a lot more research. And we need to look into the consequences of wrong decisions. And that's also why we really need to look into how to integrate. I mean, I think also areas like interpretability, explainability are very important, and also to run user tests, which is expensive. It's not that easy to publish, but I think it's important to actually show that many of the things would generalize to future tasks as well. And I mean, there's more available on our webpage. I have a couple of pictures from our team. I'd like to thank the European Commission for funding our projects. And if you have any questions, I mean, don't hesitate to contact us. And so thanks for listening. So this is a picture close by. Currently, we don't have that much snow, but these are my traces in the snow. And I wanted to tell you a little bit of a story about some of the challenges that we have. And And I hope that I got your interest in this. And I mean, now I'm open for questions.
Thank you, Henning. Very appealing, right? I'm not sure how this, your traces in the snow would fit with medical stuff. I mean, I wish I don't need to go through some of this stuff after I'm going skiing, but.
Well, I mean,
well, I'm doing this kind of traces as well, so that's okay. I'm good at it. So.
Well, if you break your leg, then it becomes a medical problem.
Exactly. So
exactly.
I can do the traces. I prefer not
you
to
produce
take the
images in that case, so definitely.
Right.
So.
Okay, so well, we are open for questions. There were several questions into the chat, so maybe well, I can ask the guys to call them directly. So I see Christian Geisler. If you want to ask them directly, otherwise I can read the question.
Is continuous learning in conflict with the certification? I mean, actually, what it's true that there is a challenge in certification that you normally need to certify a closed system. Many of the companies that certify their algorithms actually try to certify the general procedure, and which allows them, if they have better models, to actually plug in a different model. I'm not sure, I mean, I'm not an expert in certification, so I'm not sure how much that would influence this. But from what I've seen, it seems that you can actually use a different model inside an existing system as long as it respects some aspects of the risk minimization. I mean, I'm not sure if there's anybody who's really an expert. I've never gone through certification. I've worked with companies, but they've always done the certification. It's a tedious and expensive process, and it's usually not the most interesting part for a scientist. Let me see. Could you please elaborate on the challenges imposed by ethics? What would be the most important guidelines researchers must follow to always conduct an ethical approach? So first of all, if you want to do any data acquisition in a hospital, you need to make an ethics request. Most of the time, you need informed consent from the patients so that patients actually agree on having their data used for research. Many hospitals now do that on a routine basis. So the different models, there are opt-in and opt-out models. Most hospitals use an opt-in model, so the patient needs to sign. Some hospitals now inform everybody your data is used for research, and then patients can actually opt out. That's a different model that currently few hospitals use. I mean, it's important that people know what happens with the data. There are some retrospective studies where the informed consent can be waived, but that's something that the ethics commissions can also tell you more about. So you might make a request for an ethics commission, and they might then tell you, oh, in this case, you need to do informed consent. In that case, it could be waived because you're not doing any harm to a patient. So it's, for example, if it's purely retrospective data analysis, it's usually much easier than if you put any risk on a patient. Like if you use it in prospective study, where you would decide based on the data whether you get, I don't know, chemotherapy or immunotherapy. I mean, you're putting a risk to the patient, and in that respect, the risk. I mean, the ethics committee might impose stronger restrictions on what can be done. But I think it's important to follow the ethics committees, and we've actually created here in our university an applied ethics service. So we have an ethicist who actually helps us in preparing the demands, but also look into what can easily be done and what is maybe much more difficult. And there are usually, in Switzerland, there's a national ethics association, then there are regional ones. We're actually trying to also seek the contact with them. Sometimes they can block a lot of things just also because they don't really know. I mean, AI, machine learning is something that they don't necessarily know much about. So it scares them a little bit. So they also want to just make sure that everything is proper and in order. And I think looking for the contact, explaining what you're doing, checking with them how to deal with it, I think that's the best approach in my experience. So how well does explainability work in practice? There are studies that show that explanations can bias clinicians towards wrong decisions or other results that clinicians actually don't want to ponder about the correctness of AI based on explanations, since they don't have the time for that. I mean, I think there's definitely a risk when using any AI tool that the clinician might not fully look at the data. And I think any black box saying, oh, this is grade 5 cancer or grade 4 cancer, like any classification, might give you a bias in terms of your decision making. I think what we need to take into account is also that as a clinician, the clinician is the one taking a decision and he's responsible for the decision. So they actually need to look at the data. And I think sometimes highlighting specific regions might not mean that they don't need to look at the other regions, but it can give them enough information to possibly avoid errors, because even though they technically need to look at the entire images, but when we look at histopathology images, you have 20 images of 100,000 by 100,000 pixels. I mean, they cannot zoom in everywhere and look at the whole pictures. They look at specific areas, and by pointing them to the most severe areas, maybe we can make sure that they actually look at those areas particularly, and then also into the areas based on their experience. So I think it's not necessarily interpretability or explainability that would bias clinician, but it's more the AI use in itself. And I think interpretability, depending on how it is used, can actually help to avoid wrong decisions. And it's the same like uncertainty. I mean, if the algorithm actually tells you the probability of specific decisions or the most likely decisions, it can actually help a clinician also to look at a differential diagnosis in a much better way. I mean, there's definitely a risk of bias of any use of AI tools in clinical practice. Regarding integration of AI into clinical workflow, what is your view regarding determining the point at which AI can be considered ready for this? There are so many challenges that can affect prediction reliability. How do we balance risk, safeguard against error versus promise of advancing practical? I mean, that's a good question. I mean, it's difficult to say when exactly to use AI or not to use it. I think what's quite important is that people actually run prospective studies. So not only laboratory experiments, but actually test it in prospective studies before they use it in practice. And it's not only a question of pure performance of it, but I think it's more about the way in which the integration is done, so that you're aware of some of the risks and that the algorithms also look into identifying its limits. For example, if there's a new CT scanner that's not that hasn't been used at all for the training, then the algorithm should maybe flag it directly and say, oh, these images come from a machine that seems like out of range for us, or these imaging parameters. I mean, if you look at slice thickness, and if the algorithm is trained with millimetric slices, but then you have 0.3 millimeter slices or 5 millimeter slices, then the algorithm should say like, okay, this is out of our range. And I think it's important to look at these more technical parameters and not simply take an image and run the algorithm on and then give a result back. I think there need to be sanity checks that I think that's important for any integration. I think it's important to really run prospective trials before you consider any full integration into the clinical workflow.
Joris, maybe you want to answer.
Yes.
I have a question regarding medical image privacy, because medical images, medical data are highly private. Yep. And they have to be protected. The problem is that if you start manipulating the medical data to lose their personal features, then they lose diagnostic value as well. And privacy is important for the lifespan of a person. Once a person dies, maybe there's no issue for privacy anymore. Instead, such types of medical data can be very valuable for research. For example, we have recently done some work on reversible techniques for privacy protection, where you corrupt your data for a certain period and then you reverse it when it's needed. Do you think it makes sense to be used? We apply these techniques on facial images primarily, but in principle, they can be applied also to medical images. Do you think it's worth trying?
Definitely. I mean, there's a variety of things where you can possibly identify people. So not only, so if we look at medical images, most of them are in the DICOM format, and then you have structured information. You can, everything that's personally identifying, I mean, birth date and these kind of things, you can remove. If you have a 110-year-old person, I mean, you're very likely to know who the person is. So all of that you can remove. If you have images, if you have facial features, I mean, from a CT or MRI scan, you can more or less reproduce the image. I mean, you might not have the hair properly, but you can, if you know the person, it's possible that you know them. So I think some ways of looking into this can also help. I mean, it's true that if a person dies, maybe it's not so important anymore. And that's some of the reason. I mean, if you work on cancer, like high-risk patients, so people who retrospectively, well, most people would be dead by the moment when you do the analysis. Quite often, informed consent can be waived because contacting the family of the persons for informed consent might actually put more pressure on them than it helps them. So there's always the balance between risk for an individual and also the advantage. Because it's also non-ethical if you can help future patients to not use the data. So there's a lot of discussion about that as well, because it's not only the protection of the person, but also how well can actually algorithm potentially help other people. One of the things that we also need to pay attention to, I mean, even when people are dead, but if you look at genetic information, and some images might allow to actually derive some genetic defects as well. Even, I mean, if some of the histopathology data, for example, might allow you to derive genetic data, and then, I mean, it's also the children, the parents of a person. Even if the person is dead, it has an impact on the children because it might be able to identify some of the things. But I mean, that's something to, that's maybe an extreme case, and with images, that's real. But if you have full genetic data, I mean, it affects by far more than the person himself.
Thank you.
Okay. You can take one or two more questions, so then
Okay.
I think we are almost.
So what are your thoughts about the synthetic data generation for the disease with limited supply of public data? I mean, with GANs, for example, I mean, there's a lot of work now on generating data, and I think it's something that's quite interesting, and I think it's something that can help. It's again, I mean, if you have areas where you have very sparse data, you also need to pay attention to when you generate data, and it's based on very few cases, how much identifying information possibly remains in there. But it's definitely a way of generating more data and increasing generalizability of some of the approaches. The risk is, as always, that when you have only like artificially generated data, that you basically detect what your model says, but you also always need to validate that it also works on like the variations that you might have in real life data. But I think it's definitely very, very interesting field, and it would be interesting to run experiments with that and really test them on prospective data, so on unseen data that might have a variability that was not foreseen initially.
Right. There is a question also about how do you shift from let's say COCO to the medical domain, but this would also be for ImageNet, right? For the for deep learning. I mean, I would argue that ImageNet is not really good for pre-training if you want to apply deep learning onto image domain. So what would be your solution?
It's actually, I mean, the thing is that in many tasks, actually, ImageNet pre-trained models had very good performance on medical data. Sometimes
sure, because you have to do a lot of fine tuning, but just I mean, it's better than random. I agree, but I would say you may want to have some kind of more specific ImageNet or so.
I mean, it's definitely something that I mean, when you look at the literature, the results vary quite a bit. I mean, there are many people who have very good results on ImageNet pre-trained data, but then it really depends. I think what is important is to really check what do you need in your data. As I said, if images are taken under standardized conditions in terms of scale particularly, then scale is actually important for the decision making. So removing scale, making scale invariant actually reduces your performance. And that is something for histopathology, it was really flagrant because we used it on a specific task and just removed scale, and our performance increased from like 50 to 85%. So with the same network, just removing some information about some of the layers. And I mean, that's some of the risks that we have when we shift from the non-medical to the medical field. I mean, if you have enough data available, it's definitely great to train on fully on the medical data. Quite often, the problem is that there's not enough data available. And I think it's just important to be aware of the limitations that has, in particular, look at like what are the characteristics, and really look at like what are images that are misclassified. I mean, really manually checking what are the problems that you can see. And if you can identify them, then you can check more systematically to actually remove some of these problems.
Right.
What
Okay.
else do we have? It's one question, range of cost for medical software certification. Very difficult. I mean, I've never done a medical software certification myself. I've talked to people who've done it, and they said they've hired somebody to work, and it took like almost a year. So I would expect in the range of 50, 100,000 euros. I think in that range you can do a certification, particularly not the payment for the certification itself, but really having somebody fill in everything and really analyze the software. So whenever there's something changing, to make sure that you can explain what will happen under these circumstances. So it's a tedious process, and I think it varies. It has gotten more complex just a few months ago with the new regulation for in vitro diagnostics. I haven't looked in detail at like how much more complex it is. I was told that it is a lot more work to have an algorithm certified right now. But again, it's difficult for me to precisely judge that. For people who joined late, is it possible to look at the recording? I mean, that's up to you. I think the recording will be made available.
Yes, it will be made available. Joanna already puts the link for it on YouTube, so that's fine. Okay, so that's about it more or less. So,
and I mean, if there are other questions, I mean, don't hesitate. You have my email address here, so don't hesitate to send me a message, and I'm happy to respond. If there are any comments or any feedback.
Okay, thanks a lot, Henning.
Thank you very much, Henning.
Well,
really a pleasure, and
Thank you.
Hope to see you very soon.
Yep, definitely in person as well. So
in person, exactly.
Okay,
Yeah,
thank
you, Henning.
Thank you very much.
See you. Thank you.